Thanks, Eric. Mirror. Yeah, let me just. Perfect. Okay, so if I'm successful, I can get us all back on track. So I'm going to, the motivation for this talk came from a conversation I had with a font designer friend a few months ago in Montreal. And they said their font engineer is reporting that the font doesn't build with neither MakeOTF nor FontMake because the lookups overflow. And I told them to send it to me and I can fix it tomorrow. They didn't send. A few days later, I asked, and they said, oh, they rewrote the feature file so it doesn't overflow. And I figured that that's not how things should work. And as by now all of you know, we don't charge for support, but we do need bug reports to come in. So I figured that this room is exactly where my bug report audience is. And please, if you ever have issues with our tools, file a bug. We can't fix it if we don't know about it. But this presentation is about a problem that I'm sure many of you have had to deal with, lookup overflows. Who has had to deal with lookup overflows in their files? Okay, good number. So what I have here is the last stage of building a variable font from merged sources of about 20 Noto fonts. Building the whole thing takes an hour. That's a problem in itself, but I'm only talking about the last compiled stage of the thing. And I'll start it now. I think I'll be done before it finishes. So then the next problem with trying to put this presentation together was I had to draw a lot of things to explain the concepts I was going to talk about. And do I look like a designer? No. So I have to ask you all come forward because I have them all here. Okay, joking. So the problem we are dealing with is when you write something like a kerning table or feature files in the Adobe feature file format, and when MakeOTF or FontMake take this, they convert this into some internal structures that look something like this. This is, for example, a GPOS table. You have the script list, feature list, lookup list. They should sound familiar. And then in the lookup list, you have lookups. Each lookup has two sub-lookups. In this case, they are pair positioning kerning tables. One of them is your exception table. The other one is your class-based table. Now, the job of the compiler is to take this and generate a font file. A font file is just a set of bytes, one after the other. Converting this structure into the font file is a process we call serializing the font data, right? But from my point of view, from a computer science point of view, you can look at this as this. This is called a graph, a simple graph, a simple directed graph. It's simple as in there's only one edge between any two nodes at most. It's directed, which means all the edges have a direction, a source, and destination. It's acyclic because there is no cycles. The font format does not allow to have cycles. And it's a graph. The graph is the name of this mathematical object. This is a simpler graph. I named the nodes so I can refer to them. Here we have A is the root of the tree, and then B, C, and they each have two children. And the goal of this packing algorithm is to order them in something like this. The property of this ordering is that all the edges go from top to the bottom. So there's no edge going back because, again, that's part of the requirement of how these tables end up in the font file. Now, the process of converting that tree into such an ordering is called topological sorting. In this case, I used an algorithm called depth-first search. This ordering is called post-order traversal or post-order, although I reversed it. But that's the kind of thing that this algorithm does. That's not the only way you can do it. That's how currently fontTools does it. But a different order is instead of going, so that order essentially went from A to B, from B to B1, then B2, then back up to C, C1, C2. Another ordering is to say, okay, let's just serialize everyone at the first level, then the second level, then the third level. That becomes something called the breadth-first search. Now, another property of this problem is sometimes these nodes contain the same data. And by referring to the same object, we can save bytes. So instead of serializing the same data multiple times in the file, we can serialize it once and refer to it multiple times. So if you merge all the identical nodes in the tree, you get something like this. This is not a tree anymore, it's still a graph. This is how a serialization looks like. The node D here is referred to multiple times. Now, for example, this is another ordering. You can put the things together, which is not a topological sort order because the node C has an edge going to D, but it's going up. It's going backward. That's not legal. So that's how not to pack things. Another property of the problem is consider this node A that has 4 children. Some of them are larger than the other. The size here represents how many bytes you need to encode this, for example. And here's one way to encode this, and everything looks good. But if I reorder things, now all in a sudden, that's where that overflow thing happens. What's this overflow thing? Well, these edges are offsets that need to be encoded in the font file, and these are encoded as 16-bit numbers, so they are limited to 64 kilobytes. Now, if the GPOS is larger, there's a possibility that we cannot encode this number. That's when we say the overflow happens. Now, in this case, by just reordering the children of this node, I cause the overflow to happen. So if you think about it, in a case simple like this, it's always beneficial to encode the largest child at the end. If there is a solution that doesn't overflow, encoding the largest one at the end produces no overflow. So that's an insight we take. That's where this idea of packing the smallest one first comes from. Now, again, so before I was representing this kind of thing as a simple graph like this, where every edge looked like the other. Now to be able to design algorithms that take the size of the objects in consideration, I'm going to change this to something else that is called a simple weighted acyclic directed graph. In this case, every edge also has a length. I'm showing the length of the edge by just making them longer. Typically, people write numbers on them. So now, with this object, I try to come with a better packing algorithm. So here, we call this object a simple weighted acyclic directed graph. The simple there means there's at most one edge between 2 nodes, but that's also not a requirement. It's very common to have a kerning table that multiple kern pairs refer to the same variation data. So there is no requirement that there's only one node. I remove that, we get a weighted acyclic graph. And now there are multiple strategies to resolve conflicts, overflows when they happen. The first one is if you are trying to pack this lookup here and it doesn't fit, we get the lookup before it, shoot it all into their own extension table. This extension mechanism is a way to encode an offset that is 32 bits, so it never overflows. You can take a subset of the tree, put it somewhere else, and say all of that, let's encode it separately, and hope that that doesn't overflow. Problem with this is we don't do object sharing between the 2 sets anymore. These are all, by the way, all what used implemented 15 years ago. Another strategy to resolve overflows is, in a case like this, that node B might be your class kerning matrix. That node by itself is so large, it cannot encode an offset to its own children. No matter how you order them, those two are going to overflow. So the solution here is to break that subtable into a smaller one. That's where that infamous subtable clause in feature file comes from. fontTools automatically breaks lookup types into something like this, so you don't have to bother. The last strategy to resolve overflows is if you have the shape on the left, A and B both refer to C, but now the offset from A to C overflows, we can just duplicate C. Now, duplicating an object enlarges the size of the font, but at least now you can encode it. So these are the three ways you can resolve duplicates. Now, my new algorithm, which I was hoping I have fully finished here, typically I'm good at finishing things just before presentation, but this time I overshoot. Might be done by tomorrow, who knows? But the idea was to borrow some ideas from Orchestra's algorithm. Now, Esker Wicked Dijkstra is a good fella, born about 90 years ago, not far from here in Rotterdam. He's one of the fathers of computer science. He has an algorithm named after him from 1956, I think. Orchestra's algorithm is an algorithm to find the shortest path from a node in a graph to every other node. In this case, it looks like, well, on the shape on the left, the algorithm can be described as this. You take the node you are interested in, pull it up, and see where every other node stands. That's the shortest path between the original node and every other node. So with insights with this, I want to solve this problem. Now the problem is, as you can see, this is not a topological sort order. There are arcs going back. So accommodating for that, I came up with something else that, like, if there's a, I can point here, yeah. So these boxes here, they have room to fall off, but because we want to enforce a topological sort order, and this one has to stay here, they just stack on top of it. That's the idea behind the algorithm. So combining everything together, here is how the current algorithm works. It uses a DFS sort order. To resolve overflows, it first tries to duplicate objects. If it doesn't work, tries to break it up. If that doesn't work, tries to use an extension lookup type. And every time it has to use one of those strategies, it restarts everything from scratch. Now, there are multiple problems with this. That the using of the extension lookup and putting everything aside is, well, the use of the DFS to begin with is prone to overflows because you encode an entire subtree before going to the next subtree. It's very high chances that the first node of that subtree overflows. Using extensions to put everything in a different tree disables optimization, object sharing, and the whole thing is so slow. Now, what I'm working on, I want to use a Dijkstra-based ordering, which is very good at encoding things with a shorter leash first, so there's a lower chance of overflow. And then to resolve the overflow, I first duplicate the object. If that doesn't work, I break them up. However, I only have to retry from scratch if I broke up. I'm able to implement duplication without restarting. I just duplicate the object and continue the process. And I handle the extension lookups completely on a higher level. Initially, I upgrade every lookup to an extension. I do my packing, then remove the extension things if they don't overflow. So it's a completely backward operation. And the biggest problem I had testing this is I had a half-working prototype. I couldn't find fonts that overflow it. So I couldn't implement the overflow anymore. Finally, I got the Noto one does. So I have a test case now. But recently, people are building much more complicated fonts. So send me. If it overflows, send me. And that's all I had. And this took 7 minutes. It took longer, apparently. Thank you.